Hi, everyone. Thanks for coming to the last session of the day. My name is Matt, and let's get to the CHOPVAR. So today, I want to talk about the Arnold C programming language and how you can compile it to JavaScript. So quick show of hands. Are there any full-time Arnold C developers out there right now? Anyone? No one? OK, that's fair. What about for side projects, just to get away from the drudgery of using Clojure or Mal in your day job? Anyone just hacking around on Arnold C right now? No one? OK. Well, that's cool. I mean, it's a pretty new language. So kudos to everyone here for staying on the bleeding edge instead of learning ECMAScript 2018 or whatever Angular is requiring these days. Anyway, the Arnold C community is pretty small right now. So I just wanted to show you that there's something to this language and show you that getting started is nice and easy. So Arnold C. It's an imperative programming language created by Lauri Hartika. He's Finnish, I believe, where all the keywords are based on one-liners from Arnold Schwarzenegger movies. Since most of you aren't Arnold C programmers for your day jobs yet, I've prepared an intro to the language. Don't worry, by the end of this session, you will all be experts. So here's the archetypal hello world in Arnold C. So every Arnold C program begins with the it's showtime keyword, and it ends with the you have been terminated keyword. To print out anything, you use the talk to the hand keyword, and it's simple as that. The only variables that are available in Arnold C are unsigned integers. So in order to declare a variable, you use the keyword hey Christmas tree from the extremely important Schwarzenegger movie Jingle All the Way, and you declare the initial value with you set us up. Note that, again, these are only unsigned integers, so if you want to use decimals, we're simplifying the language for you. In addition, there's no concept of Booleans in Arnold C. So if you want to declare something as true or false, it works the same way that C does, where 0 is interpreted as false and any other value is interpreted as true. Luckily, you don't want to be writing 0 and 1 in every instance when you're writing your Arnold C programs. So they're very helpful macros of I lied, which is the macro which will just convert to 0, and no problemo, which will be converted into 1. So that's cool. If you want to do more complex math, you have the ability to do that. You have to use the get to the chopper keyword, and then you set the initial value with here's my invitation. And then you do math on it. You perform various calculations, one on each line. And then once you're finished with your stack of operations, you use the enough talk keyword. So one thing that's important to note is that in Arnold C, there is no such concept as order of operations. Everything happens from left to right in terms of the call stack. So in this case, we're going to be declaring our variable A. We start off by setting its initial value to 4. Get up is the keyword for adding a value, so we're going to be adding B to it, and your fired will multiply that value. These are the total number of operations that you can do for math in Arnold C. So plus is get up, minus is get down. To multiply, you use the you're fired. Dividing is he had to split, and the modulo operation is I let him go. Modulo is actually really new to the Arnold C specification. It was only added a few months ago. So it's an actively developed programming language, so that's really important as well. So this is an if statement in Arnold C. So if you want to check on whether or not a value is true or false, you use the because I'm going to say please keyword. If that is true, then you can perform a set of statements, and then your end curly brace is you have no respect for logic. If you want to use the else statement, then you just use the bullshit keyword. That's the only profanity in this talk, so I'll do my best. And then you have your other options. So the only thing that you can do for your conditional is to test whether or not something is true. So hopefully you're using the I lied and the no problemo macros in order to make this as efficient as an Arnold C program that's available. So here's how you declare a function in Arnold C. You use the listen to me very carefully keyword, and then you perform whatever operations or statements inside of your function, and then you end your function with hasta la vista, baby. To invoke the function, you simply use the do it now keyword, and it's as simple as pie. If you have parameters, then you have to use the I need your clothes, your boots, and your motorcycle keyword. So in this case, the add5 function takes a single parameter, which is num. But if you had multiple parameters that your function would take, then each line or each parameter would have its own I need your clothes, your boots, and your motorcycle keyword that goes along with it. So in order to invoke a function, you just simply add in the parameters afterwards. So in this case, we would be adding 5, and we're just passing in 8, which is our number. So the result of this function would be that it would talk to the hand for the sum, which would be 13. If you want to declare a variable from a function call, then you have to use the give these people air keyword, which determine after you have defined all of your function parameters, and that indicates that this is a non-void function. In order to return an actual value, use the I'll be back keyword, and then to use it, you simply, in order to declare a variable from a function call, you use the get your ass to Mars keyword. And so in this case, result will be the result of calling the add5 function, passing the 8 parameter, and then you can perform whatever actions you want with it. So the talk to the hand would actually print it out. So the only looping structure in Arnold C is a while loop, because that's all that you need, really. The stick around keyword will continue to execute as long as value is true, and you end your while loop with a chill statement, or keyword, sorry. So that's basically everything that's available in Arnold C. So if you're used to other programming languages, I'm sure that you've done a fair amount of bike shedding. By day, I'm a JavaScript programmer, so there's a lot of stuff that's controversial coming out in the new versions of JavaScript, the ECMAScript 2015 ES6. So all of those features, all those controversial elements, like classes, modules, don't exist in Arnold C. So you can really focus on the core of your programming. Other things that are just eliminated so you can just focus on your work, things like decimals, you don't really need anymore. Strings, they're just all gone. So you can just focus on the work at hand. It's streamlined for maximum productivity. If you want to know more about Arnold C, the GitHub page has great documentation on everything that's possible with the language. And it includes the most important section. So for each keyword that's in the language, it will show you what it does and the catchphrase that it came from. And when you click on it,
listen to me very carefully.
It'll actually show you from which movie the keyword comes from. I don't know why other languages don't do this. It seems like a no-brainer to me. And this is really valuable as you start to do your porting, because you have to know whether or not it's from Total Recall or Jingle All the Way. And in fact, some local companies are getting in on the action. So Garmin posted earlier this year in their forums about supporting Arnold C for their Connect IQ platform so that your watch can be powered through all the great features that I've already talked about. They added this feature in April of last year. Nick Kroll might be able to talk a little bit about it. I think that he posted. I'm not sure about the specific date, but anyway. So the Arnold C homepage also has some really good documentation on how to get started. So all you have to do is create your file, your hello.arnoldc, then download the Arnold C jar, run Java. OK, so this is where we run into our first problem that I can see with the Arnold C language. So as modern programmers that are interested in the cutting edge of computing, as we are, we can't use Java for anything that's this groundbreaking. And even if you wanted to use Java, we would have a real problem. Because the JVM is an amazing piece of technology, but if you know one thing about Arnold Schwarzenegger, he simply can't be contained to a virtual machine. Luckily, there's a solution in place that doesn't involve John Connor, time travel, or direction by McGee. Instead, it simply relies on the power of another extremely powerful tool, compilers. So let's talk about compiling from one language to another. So a traditional compiler like GCC or Clang will go from a high-level language like C and run it through the compiler and produce assembly, machine code, or bytecode, something that the computer can execute more natively than a higher-level language. There's another type of compiler, which is one that goes from a high-level programming language to another high-level programming language. Sometimes these are known as source-to-source compilers. So in this case, we have CoffeeScript on the left, We'll run it through the CoffeeScript compiler, and this is the JavaScript that gets generated over on the right-hand side. Some people refer to these as two completely separate categories of tools, compilers versus transpilers. I don't really think that there's much of a difference, and for the sake of this talk, I'm going to call everything compilers. So a brief history of compilers. The first one was created in 1951. It was called A0, and it was written by Grace Hopper for a specific machine, the UNIVAC 1. In fact, Grace Hopper invented the term compiler. She also wrote a very important tool called Flowmatic, which was the predecessor to COBOL, and it was extremely popular at the time. It was the first language that used English-like keywords for the language's keywords. She argued that folks didn't want to write code, that they wanted to write code in a higher level language and didn't want to have to write machine code or assembler for a very specific program. Her bosses said that it wasn't possible, so she just went off with a team and did it. I like to think of Flowmatic as the world's first transpiler because that it provided an abstraction on top of the machine code that was being written by humans at the time. So this is really interesting. I was doing some research on Flowmatic, and I found this brochure on the Computer History Museum's website that they archived kind of the marketing pamphlet for why a team would want to begin using Flowmatic, this new language. There's some key benefits to the language, and going through them, I think a lot of these might sound familiar. So some of these unique savings that Flowmatic provided is that it freed you from the clerical drudgery to do more creative work. Right? You didn't have to spend your time focusing on the actual symbols that you were typing. You could look at the higher level. It broke the communication barrier between programmers and managers. Isn't it good that they solved this in 1951? Dramatically reduces training time, right? So now that you're working at this higher level, you're just going to get an order of magnitude solution, right? This sounds really familiar. We've been trying to solve these problems for years and years. We haven't quite gotten to it yet, but this is just the concepts were pioneered by Grace Hopper. It's her world. We're just living in it. So anyway, let's talk about what actually goes into creating a compiler. A compiler has three important parts: the lexer, the parser, and then the code that translates or generates additional code. So let's start by taking a look at the lexer. So you can think of a program as a string of characters, and you can break them apart down into their atomic tokens. So white space is also a token, but in most cases it's thrown out as not being meaningful, unless you're working in a language that has significant white space, your CoffeeScripts, your Pythons, etc. So this is what the lexical analysis for an Arnold C program might look like. Get to the chopper is one keyword. A is another keyword that just happens to be a variable. And then enough talk signifies the end of your variable assignment. So that's its own important token. In other languages that are slightly older, a little bit less inferior, they might have curly braces or semicolons or things. Like, we don't need those in modern languages, as Arnold C is proving, but that's simply another token that exists. So here's what the lexer converts these tokens to. Note that all of those other items, like white space, they get thrown away. And that's why so because those unimportant tokens get thrown away during this step is why you can have arguments with your coworkers about whether you should be indenting with tabs, 2 spaces, or 4 spaces. The lexer simply doesn't care. So the next step in the compiler's construction is parsing. So let's take this math statement again, where we're taking A, adding 4, or setting it to 4, adding B, multiplying by 2. So some of these bits are only useful to close previous expressions. That's enough talk. So we can drop them from the parser. And the next thing we can do is we can take these expressions and arrange them into more of a tree structure. So it might kind of look like this. What the parser actually sees are just the lexical tokens, those keywords that were defined and identified by the lexer in the previous step. The actual strings in the source code aren't really used for this part yet. So this is our abstract syntax tree. It's also known as an intermediate representation or an IR. So now we can generate some new code. In our case, we're going to be transpiling it or compiling it into JavaScript. So we just need to take the AST and convert it into syntactically valid JavaScript. So again, here's our AST. First, we have this assign variable section. We set the initial value and apply a set of operations against it. So that might look something like this in JavaScript. We use the var keyword, set an initial value using equals, and then apply some operations. If we actually convert it into valid JavaScript structure, it might look something like this. Although because that it's JavaScript, we have to add in those weird semicolons and stuff. Side note, once you start coding all of your applications in Arnold C, you're never going to have to debate with someone about whether you should be adding semicolons to your code, because it's not even syntactically valid in the language. So again, we've just saved so much time by coding all of your stuff in Arnold C. That's really important. So once we've generated what the structure of the code is, we can just drop in the actual values from the lexer. So we can take those tokens and replace them with the actual values from the string, and then we're good to go. And by the way, there's no one proper way to do this. The code could ostensibly also look like this if you wanted to use some of those fancy ES6 features like the let keyword, or put everything onto a single line. You can do whatever level of optimization that you want to do here. You just have to make sure that you're not breaking any of the characteristics of the original language whenever you're generating your code. For example, we couldn't do this in JavaScript without the parentheses due to the way that the JavaScript language honors the order of operations, whereas Arnold C decides to go just tread its own path. So that's the basics of writing a compiler. You're responsible for lexing, parsing, and generating code. There's also tokenizing, creating your abstract syntax tree, and then generating your sources. So a huge caveat for those of you that have formal knowledge of compilers, I'm skipping over a whole bunch of stuff. I never took a compilers class, and I'm a JavaScript programmer, so there's a culture of just inexperience that goes around. So modern compilers do enormous amounts of optimization that we're not touching on here at all. So dead code elimination and function inlining are all things that I'm just skipping over here. Semantic analysis also I'm not talking about. So that's stuff like type checking, identifying if you're using a variable before you've declared it, things like that. If you want to know more about how modern compilers work, there's a really great set of lectures on Coursera. Or you can just walk around the hallways of a college's computer science department and start yelling Dragon Book. And if you see someone screaming, then they know about compilers and they learned it the hard way. So that's your crash course on compilers. Now let's write one. You wouldn't want to write the entire lexer and parser yourself because that stuff is hard. So luckily, there's a number of frameworks that are available that allow you to define a domain-specific language for your programming language, and then you simply supply the translations yourself. So to do this effectively, we have to use a couple of tools. Unfortunately, none of them are yet written in Arnold C, but there are some good ones that are currently available in other languages. So for years, the go-to programs have been Flex and Bison that help out with these. These are tools that are written in C, and they help generate lexers and parsers. Flex is the tool that performs the lexical analysis, and it tokenizes a program. And Bison takes those tokens and generates a parser that you can use to perform translations. But because I'm a JavaScript programmer, the latest in these families of tools is Jison, which is simply a port of both the functionality that Flex and Bison provides, and it makes it available in JavaScript, and that's what I'll be using to convert Arnold C code into executable JavaScript. So Jison was created by Zach Carter. He works at Mozilla. He created and maintains Jison. He wrote it for a compilers class a couple of years ago, and it's actually the same tool that the CoffeeScript project uses for its compilation step. If you're familiar with NPM, you can then simply install it as any other node package. And here's the shell of a Jison program. You simply pass a structured grammar file, this grammar.json file, to the library, and it generates a parser for you. You then run that parser against your input string, your original Arnold C code. So let's take a look at what's inside this grammar file. So there's 3 sections to a grammar file. The format of this dates way back to the Flex and even earlier days. The top part is called the lexer. This defines the keywords and tokens for your program. The next part is the language grammar itself. These are the rules for what kind of statements are legal syntax in your input program. This might look very similar to BNF syntax or structure if you happen to do that sort of thing during schooling. And finally, you provide a set of transformations that are going to be applied to that abstract syntax tree. In the case of Jison, we'll be using JavaScript to do this step. So let's start with the lexer. This is simply a set of mappings that determine what tokens mean what in your language. Everything needs to be accounted for, so keywords, punctuation, and each of these tokens will get a name. You can also use regular expressions to define your parser, which you'll probably need to do for things like numbers, variables, strings, etc. And most lexers are also going to have these sections, which are set up to just ignore and drop white space, as well as take the end-of-file token into account. So here's part of the lexer for Arnold C. As you can see, most of these tokens are keywords. Arnold C, like most modern programming languages, has very few extraneous braces, semicolons, or other diacritical marks to get in your way. And you might also notice how the regular expression for number doesn't include a decimal. As I noted, all programs, or all Arnold C numbers are unsigned integers. You're not allowed to use decimals. It's really the essence of simplicity. So the next section is the language grammar. Basically, you take the tokens that you've defined above, and you compose them into more complex data structures and trees in order to generate your AST. So basically, on the left-hand side, you name an expression, so something that is a higher-level abstraction. This might be your while loop, for instance. On the right-hand side, the token part, you define what constitutes that expression. These usually reference some of the tokens that you had defined above, or some of the other expressions that might have been defined somewhere else. And then inside the braces, you put the code that you want Jison to execute whenever it's translating your input sources into your transpiled code. And that's where the JavaScript magic happens. You can also define an expression by itself recursively. This is really useful when you're creating trees of statements. So here's an example of an imaginary language's grammar for an expression. So an expression can be two expressions, plus, minus, divide, exponential, to each other. It could simply be a number, the irrational number values e or pi, or you could use parentheses to enclose an expression itself. And these can reduce themselves as many times as you want, which allows you to put multiple parentheses around a single expression, and it's still considered the same type of thing in terms of how the AST is going to parse it. So each of these expressions will have some code that's associated with it, in this case JavaScript. And here's what that JavaScript would look like. So there's a couple of magic symbols in here. The dollars doesn't mean that we're in an Angular or a jQuery world. Instead, it just represents parts of the right-hand side or the left-hand side of the expression. So the double dollar means that's the left-hand side of the expression. So that's what we're actually going to be defining. The $1 and $3 are the first and third items on the right-hand side of the expression, whatever they happen to be in the actual value. There's a few other special elements that we'll talk about a little bit later, but these are ways of grabbing inputs from your input string and passing them to your code generator. So structurally, you can write all of your JavaScript code or your executable translation code inside of this JSON file, but it's really difficult to use their appropriate tooling. It's in a different syntax, etc. So what I generally do is extract those JavaScript translations to a separate file. So in this case, we'll be defining them in a separate file just called ast.js. You can export it using standard CommonJS or Node.js export behavior. And then in your actual transpiler, you just simply associate the parser with the objects that you've defined. You can note the YY. It's a convention that dates even back beyond the Flex and Bison days to another language or to another parsing tool called YACC. So I kept noticing these external files that referenced all of their elements as YY, and I was trying to figure out why that happened. So this is from the YACC manual, which dates back to 1978. And notice the section here that says that the parser only uses names that begin in YY. So you should avoid using such names. It's a reserved section of the keyword. So this is a lesson both in the power of names as well as the legacy that decisions that you make for your software can have. So just a bit of advice, when you begin writing your Arnold C programs, you probably want to give some thought as to whether people 37 years down the line will understand the names and variables that you've defined. If it's a long-running enough program, then you might have that opportunity. So I would recommend avoiding using ephemeral words like YOLO or swag or React. So here's our program definition. Notice that we're taking the $1. These are the methods that are being declared before the main. And then we are taking the methods that are declared after the main function, so the it's showtime and you have been terminated, and we're moving them up to the top of our compiled code. In essence, we are hoisting them above the main program definition. It doesn't have to be done this way, but this just happened to be the way that I wrote the interpreter. Then we're taking the number 3, which are the set of statements inside of the main function, and we're just executing them one after another. You might also notice the @2 and @4. In Jison, these represent an object that contain the line and column coordinates of the element in that position on the right-hand side of the token. So these are going to be useful whenever we want to create source maps, which I'll talk about in just a second. Here's a list of all the possible statements in the Arnold C Jison code. These are the leaves in the trees of the statements that we're going to be generating as part of our AST. It's kind of an eye chart, but you can kind of see what the pattern is. So for each of these kinds of statements, we call out to a function that's defined on the YY object, and we pass in the coordinates, token values, other information that's going to be needed in order to transpile from Arnold C code into JavaScript. You might also notice that there's 2 definitions of assignment expression, so one that has ops and one that doesn't. These are calling the same JavaScript generator. It's just that one of them passes in the empty array, so the set of operations that are going to be called whenever you are assigning a value can either have 0 or a certain number. This just allows us to reuse the same code generation block for 2 different types of expressions. So here's an example of what that translation code for the print expression, also known, the talk to the hand keyword. I'm writing this using ES6 classes. I just found that it was a bit easier to work with an object-oriented feature. So in this case, the important part is that we're newing up one of these objects. The data goes into the constructor, which also includes line and column information. And it also includes the value of the thing that we actually want to print out. So that's the hello world string that goes into there. There's also a compile function, which when you call it, actually produces the generated JavaScript code. So in this case, we're just using the standard console.log that's available in JavaScript. And in our top-level class, this is simply abstract. So here's kind of what's going on. So once Jison generates its source tree, it's going to walk it and produce the intermediate representation. From there, it calls compile on each of these sub-elements, and we new up a bunch of those objects. We call compile at the top level, and then it'll do its thing and call compile on each of those sub-children all the way down through your entire AST leaf node. And you can see that's all that the main expression in this case is doing. It also adds an IFI for modularity around the code because JavaScript, but it's just taking all those statements and compiling them. And it's running them inside of a map function. So what you get back from the parser is a string that represents your transpiled code in JavaScript, or you get an error if there's a syntax failure, parsing, et cetera. And then you can write that to a file or kind of do whatever you want with it. So talk is cheap, so let's actually see what this looks like in practice. So I've got, let me go to, sorry. OK. Sweet. So let's look at the examples. So this is our hello world. Actually, I need to indent this properly. It doesn't matter for the compiler, but I want to keep my code clean for Arnold C. So this is just your standard hello world. In the case of this transpiler, the transpiler itself is available as ArnoldC.js, and then you pass in the input string that you want, and it'll do its thing. So what it generates is both hello-world.arnoldc.js as well as that .map, which is the source map file. And if we look inside of here, we can see what actually gets generated in this case. So we have our code, and then the important part is this console.log. And we can just run it, and we have our actual working hello world. So that's important. If we want to look at another one, we can take a look at this method. So in this case, I need to do this again. So we have declared that we're going to be calling the modulo 2 function. And in this case, I'm actually going to change this to hello. I will rerun. Oh, no, I did that wrong. Wait, did I do that wrong? Sorry. No, we're good. I'm trying to execute. So that obviously won't work, but this will work. And so we can kind of see how this all functions. And if you want to look at the generated code, it just defines the function, and then it executes it afterward. So there's a whole bunch of examples that are available here, but one of the important ones, so if let's take a look at the square loop. So this has a little bit more complexity to it. The important part is that we are starting off with loop. So loop is true, and it goes from 1 to 10, and will execute and print out these squares for each of the values between 1 and 10. And then for each of the values in our index, it's going to add the value, and it's going to print it out. So the proof is in the pudding. And hey, it actually worked the right way. Sweet. And then the most important one for those of you that are going to start looking into the burgeoning world of full-time Arnold C programming is the FizzBuzz implementation. So you might have seen this on programmer interviews where you have to print out the numbers 1 through 100. If it's divisible by 3, then you print out fizz. If it's divisible by 5, then you print out buzz. And if it's divisible by 15, then you print out FizzBuzz. So the implementation for FizzBuzz runs through the is this less than 100, and it's using the proper macros for no problemo, which is really important. And here we can kind of see the list of code. So one thing that's important to realize is that this isn't really idiomatic Arnold C anymore, because at the time that this was written, there wasn't a modulo keyword that was built into the language, so they had to implement it themselves, which is almost 30 lines of code, which we can now finally get rid of thanks to advances in the programming language. But if we run it, then we should be able to see that actually does the right thing, which is pretty important. So so everybody's going to be ready to ace their programming examples now. Sweet. All right. So that's cool, but you might have seen those .map files that were being generated. Those are source maps. So a source map is simply a file that allows for a bidirectional mapping between an original source file and a translated version of this. So in this case, we're using it for a Arnold C to JavaScript compile it. But it's useful for any number of use cases. So if you are minifying your JavaScript code, if you are transpiling it like we are in our case, or even if you're concatenating multiple files together, you might want to produce a source map so that you're not having to debug generated or compiled code when you're running inside of a browser or some other optimized environment. So here's the last part of the compiled JavaScript file for that FizzBuzz example. The special comment source mapping URL. This is a reference to a file, which is the fizzbuzz.arnoldc.js.map. Here's what that source map file looks like. Everyone good? Luckily, you're never actually going to have to write one of these yourself. There's a module that's available in NPM that you can use to generate your source maps. It was written by Nick Fitzgerald. He's the co-author, along with the gentleman at Google, of the source map specification. Nick also works for Mozilla. So to use it, you simply you require it, you install it the way that you normally would for any other node module. You grab a source node object, and then you new it up, and you return it. So rather than returning strings, you return the source node objects that takes the line and column position from the original source, the file name, and the compiled string. So In order to incorporate this into our transpiler, we can add some helper methods onto our abstract parent class to allow us to generate source nodes very easily. This can be chained, so in the main expression, for instance, we can start with our immediately invocable function expression and then add in all those child statements, each of which are now going to be producing source nodes as well. You might also notice that compile has some has some parameters, and those are getting passed into the source node file generation. So now you have your AST, but instead of returning a bunch of strings whenever you run compile, it simply returns a set of source node objects. So once you're done, there's an API in the source node object that allows you to grab both the compiled sources as well as the source map. You just have to write them off to separate files, and you're done. And then you can just deliver them with your compiled code. So whenever you open up the developer tools, the browser will read in those source map files, and everything will just work out of the box. So to see what this looks like in practice, we can take a look at a couple of tools. So I'm going to start, actually, by going back to my examples. And let's see what's in our test. So in this case, this is just a standard HTML page where I'm loading up the compiled version of that FizzBuzz program. So if I open that up, and if I go to the console, so you can see that this is actually performing the work here over on the side. Oh, let me, I'll do a view source so that we can see what this is. Yeah, there's nothing special that's in here. If we look at the .js file, it doesn't work. But the important part is that if you see, you can see that these are referencing the actual FizzBuzz Arnold C. Actually, let me try this again. Here we go. So now it's, after refreshing, it's actually showing the .ArnoldC files. And if I click on one of these, then you can see that Chrome's DevTools have loaded both the compiled JavaScript as well as the Arnold C version of the code. And this is important. So now I can take a look, and I can actually read through the original source files, as well as I can put breakpoints in. So I'll refresh the code. And so now I've got breakpoints, so I can actually see, I can step through the code the way that I normally would, and I get access to all of the developer tools that Chrome or Firefox or whatever technology that you want to use provides for this. So I can step into my code, I can step out. So I never have to work in, I never have to toil in the drudgery of JavaScript again. Even my developer tools are working in Arnold C. So that's really important. You can, put in breakpoints. All this stuff just works great. The other thing that's useful is to take a look at the source map visualization. This is simply a tool. I didn't write this, but it allows you to, you can pass in a source map, and you can see what code gets, what the original source files look like and how they translate to the generated code. So in our case, we'll go to, the examples. So we'll take the compiled JavaScript and the source map file. So, and then you can see, so again, we start by taking the functions that were up top and we're hoisting them in kind of interesting places. But you can see this is, the Hey Christmas Tree keyword is simply defining our variable. N, our initial value, we're setting the values, no problemo maps to true, etc. So this is just a good way of identifying what these source maps are doing. And if you ever happen to write a compiler that uses source maps, this is invaluable in debugging purposes. So that's important. Let's go back to the code. So hopefully by this point you can kind of see what the power of Arnold C has to offer for you. But a fantastic language standing on its own isn't going to be enough to convert a number of people. If you want to know the history of a great language that died due to a lack of tooling, you can just go find a small talk programmer. So before you can go to your boss and convince them that it's time for you to abandon Clojure and migrate your projects to Arnold C, you have to make sure that all of your workflow tools support this fantastic language. But luckily, the ecosystem around Arnold C is great and getting better. So traditionally, the compiler has only worked in Java. But thanks to Browserify and other tools, we can generate executable Arnold C code inside the browser itself. So I'm going to show you what that looks like. So this is simply the in-browser compiler. I'll run, oh, wait. So it's running browserify against the Arnold C code, and it'll open up in the browser. So in this case, on the left-hand side, it's simply our code. So, and if I start writing, and if I let it go for a second, what's the problem? Oh, I have accidentally not used capital letters for everything. OK, so now this is actually generating in real time your executable Arnold C. Because I don't want to bore you too much, I'll show you some examples. And then if I open up the developer tools, I can actually run this, and it'll do the right thing. And we can actually see that it's running stuff automatically. The square loop, all of this just works out of the box. So this is expanding at the power that Arnold C provides for you, which is really, really important. You might also be using a task runner like Gulp. Luckily, there's also an Arnold C plugin available for that. So let's take a look at that. Oh yeah, so this is just how you use it. It's more interesting if we take a look at a project that's actually using it. So in this case, so this is just a really complex Gulp file, but the important part is this Arnold C line, and then this is the actual piece where it's finding all the Arnold C files, initting them, and then running the Arnold C compiler against them. So in this case, I'll begin by running it. It's going to do its thing. That part isn't important. I'll just run through localhost 4000. Cool. So this is a program that simply, it kind of shows different things that you can do in ES6 or CoffeeScript or TypeScript. If we look at the sources tab, we can actually see the sources. So we can see like the TypeScript code, et cetera. But the Arnold C code is also showing up here, and we can do our same behavior. So in this case, again, it's just printing out Arnold C. One of the interesting things about this particular example is that this is actually an AngularJS controller that's written in Arnold C. So if you were like me and you were kind of upset that Angular 2 is moving towards using like TypeScript as its compiled to JavaScript language, don't worry. Arnold C still has you covered. You can still write your Angular code using those tools. You do have to do some tricks, like you can't set objects, so you end up having to you have to call the eval function in a few places, but that's just a limitation of JavaScript, less than an indictment of Arnold C itself. But it does work, so that's important. Let's go back to our keynote. Or maybe you're a little bit more modern and you want to incorporate Arnold C into a larger project. You might be using a module loader that allows you to take your code and smush it into something that runs in the browser. That might be Webpack, and Arnold C also has you covered there. So here's your Webpack loader. I'll just show what that looks like in code again. So there's not a whole lot that's to it if you've used Webpack, but again, it just finds all the Arnold C programs and it runs them through the Arnold C loader. And when we run this, it runs it on localhost 8080. So again, this is, there's not a whole lot that's actually happening here, but if we refresh the code, we can see that, again, the most important functionality, which is FizzBuzz, the source maps all work the way that you would expect them to, and it just works out of the box. So if I make a change to the code, and if oh, right, so there's a bug here. So it actually says buzz fizz, and I don't want that. So instead, I'll just change it to FizzBuzz. And now if I rerun this, Webpack has already done everything, so it's already changed it to FizzBuzz. So you can tell that like your workflow is going to just be enhanced by starting to use Arnold C everywhere rather than having to use your other languages. And here's something that no other language has that I'm aware of, which is the Arnold C speaker. And I'll just let this speak for itself. So let me go back to the code. So I didn't write this, but it's just such an important tool in the ecosystem that I can't not show it. So this simply allows you to take some code and...
It's showtime. Talk to the hand. You are terminated.
You can run
showtime.
Any Arnold C program that you want.
Talk to the hand.
Get your ass to Moss.
Do it now!
I want to ask you a bunch of questions.
I'm just going to let this run the entire rest of the night. So one thing that's going to be really helpful, again, just a bit of job hunting advice. If you blindfold yourself and listen to an Arnold C program, see whether or not you can actually interpret it yourself. I think that's really going to set you apart from the rest of the, everyday Arnold C programmers that are just doing this for their day job. This is really going to prove that you have a passion for the language, which is going to be really important in the hot-paced Arnold C world. So in the rare case that you don't think that Arnold C is the right programming language for you to do your work, that's OK. You can take the guts of the compiler, which is available on GitHub, and implement your own compiled to JavaScript language. Or you might want to do something that's completely different. Maybe you want to write a domain-specific language that can be executable in the browser. Or maybe you have lots of code that's written in a legacy language, and you want to port it so that it runs on a different platform that might be a little bit more long-lived. Or maybe you just want to have a little fun, and that's OK too. But whenever you're ready for a truly powerful language, Arnold C is going to be there waiting for you to recall it, totally. And that's all that I have. Thanks, everyone.